Thanks for tuning in person and online. It's my pleasure to be here. It's a wonderful week in Tokyo. Thanks for John Gang's general intro. I'm Lexing from the Australian National University. Some of my colleagues and students are actually also online, and they might help me answer questions if you have really tough ones. So just a brief word about us. The map is not super visible like on this projector screen. We're in Canberra, the national capital that not many people have been to. Of course, Riken has many academic connections with Australia. We're happy to be part of your international network. As this Venn diagram illustrates, my lab currently work like on 3 bigger areas. Given Kai Zhang's very intriguing talk just now, I'm going to avoid the red circle, which is our LLM related work on interpretive machine learning with a purpose that we've been looking at surveys too. But and then the bottom green circle is interdisciplinary AI and interactive visualization, which I hope to show a teaser of at the end. But I think the the topic that's of most interest to this audience in terms of both methodology and style of questions is machine learning attention markets. So that's the blue circle on the top, and let's spend the next 50 minutes on that. Here's a few basically stage setting talking points to orient us into thinking about attention as a scarce resource. Each of us is no stranger to the constant deluge of information across many sources, from entertainment to news to our daily research work. And in fact, this has been articulated very well by Herbert Simon, Nobel Prize and Turing Award winner back in 1971, saying that the abundance of content implies the scarcity of attention. So for us individuals, there's too much that I could pay attention to, but which one should I? For groups, collective behavior is now a crisis discipline. Ever since Cambridge Analytica, but perhaps quite a bit earlier. For this work, at least the front part of this work, our empirical work has been focused on YouTube videos. I'll tell you why. And the fun thing in my lab for a while, for the last decade, is that we actually watch YouTube videos for work, and we claim that we know a lot about them, perhaps more than most people, like even people in Google doesn't do this kind of analysis. For this particular talk, I'm going to try and answer the following questions: how do attention evolve, and what explains it? And can we predict it? And then what are the properties of the whole ecosystem around attention as a market, involving us, a lot of us as daily users or consumers of content, producers of content, mediated by platforms. And I guess each question for this day and age is, what should regulators do in this space as a sort of, there's lots of AI and machine learning being applied, but even the current or the regulations in the last few years, none of them were based on actual computational or scientific insights about how things work in large scale. And our long-term agenda is hoping that we could shed some light on that. But I think delivering is sort of a long interdisciplinary journey that I'm happy to talk about outside this talk. All right, so here are the 2 main parts. The first part is looking at attention evolution of online items or viral videos and how they got viral. The style of the first part is measurement studies and machine learning models that are designed and applied to empirical data. And then the second part is looking at attention as a marketplace, basically how to describe the supply and demand of attention as an economic system. Does it have equilibrium? Are they reachable? What can we say about these? So this is computational economics, games, and online optimization, as some of you might be familiar with the underlying techniques, even if looking at attention as a market is somewhat new as a new problem domain. Okay, this picture tries to illustrate the type of data we look at. On the left is the #1 pop song from the last decade. And for a long time, you can actually view this green curve underneath YouTube videos, where if you just click and expand it, it shows you the number of daily views for each video. And you can see the attention kind of trends up and then slowly trends down. But even at the bottom, there is more than almost 1 million views each day. On the right, there is the pop song of 300 years ago, and there's still ongoing attention on this kind of songs. And it doesn't go out of, it doesn't really age, right, after 300 years. So how do we think about item popularity? Before our work started around almost 10 years ago now, the traditional people have applied, I think, all sensible statistical models and time series models to this, right? The basic intuition can be past popularity predicts future popularity. And also content, people, and community features should all play a role. But then the messages from there were actually mixed. People find some predictive power, but also large variance. And when I was working with the US Air Force Scientific Research Office, the program manager keep asking me whether I can use audio, video, and text content to predict how viral a video will be. My answer was actually kind of no. Because back in those days, the automatic understanding of video and audio and text are far behind what they can do now. And also we kind of observed that whenever you have behavioral signal, it's much stronger than what you can glean off the content. So I think even right now, computer judgment of how attractive a piece of content is still not quite there. Right. So the bottom are two plots or showing examples of what we observe in terms of video popularity as a time series or daily views. So they are multi-phased and it can be sort of a result of internal processes, right? So somehow, for example, on the left, there's the kids playing gymnastic video that gains popularity. On the right, there is almost a cyclic pattern. And if you look at what video it is, it actually explains what's happened. It's an instructional video of how to vent your portable air conditioner. And the peaks correspond to the summers of the Northern Hemisphere. And you can see the peak actually growing over the years, maybe a sign of global warming long time ago, unfortunately. All right. So fast forward a few years, we were the first to look at time series as basically a process that's driven from external signals. We posit that one cannot know what happens in the outside world that's outside the platform. So here's the mental model. So someone, for example, shares and talks about a particular video or some external event happens, such as earthquake or a heat wave. And then this propagates into the social media platform, which consists of several factors such as network effect, system memory, what kind of content, is it news that gets forgotten very fast, or music that doesn't really get forgotten and people go back to it, and then some intangible version of content quality, right? And as the result of this, the continuous interaction of this will be the green curve that we observe and can get from, I guess, cleverly looking at the web page of the YouTube video. So here's the mathematical model. It's basically an integral equation where the quantity xi on the left is the popularity as a time series. And then it is the result of S of t, basically how many people share this video or talk about it outside, with a multiplier. The integral term basically encodes the history of society itself. Basically, it captures how fast the attention on the content decays, right? And a number of other factors. So this is sort of a mouthful, and how do we get it? So this is basically a result inspired by what's called self-exciting point processes, and we gave it a cheeky name, Hawk's intensity process, nickname HIP. So point process are basically discrete events in continuous time, and Hawk's process is basically basically one more events begets even more events with a time decaying probability. So even if you have not dealt with point processes, in research, you probably would have heard about some processes which encodes people arriving at bus stops and so on. Those are uniform rate. But picture on the lower right-hand corner here, it's basically Hawk's point process that triggers subsequent event, but also with a time decaying probability. So then the integral equation model shown on the last page was obtained by taking expectations of the stochastic event history up to time t. So that's taking expectation of a random number of random events at random times. It's a mouthful, but it's not too hard to do. Even for us at the time that we didn't have deep expertise on stochastic processes. So if you trust me, here's what happens if you apply this model we essentially estimate this model for every single video and the first 90 days of its history. Then we can essentially project this messy looking integral equation into a two-dimensional plane in order to explain what happens. On the y-axis is this multiplier mu in front of how many sharing is happening outside. So intuitively, we call this larger mu being more promotable, the piece of content. And the x-axis is what we call endogenous response. So the intuition is basically how many views would a unit of promotion, external promotion generates. Mathematically, it's basically the impulse response of this integral equation, which is a linear time invariant system. I was happy to go back to my electrical engineering roots about to interpret this quantity, but moreover, I think it's nice to have interpretable results. So all marketers will dream to have videos on the upper right-hand side. So let's look at a few examples to see what different areas of this scatter plot might correspond, right? This particular video on the upper right-hand side is the Ice Bucket Challenge compilation by a bunch of celebrities. A lot of you might be old enough to remember this sort of wave of ice bucket challenges in order to raise awareness for rare disease, right? Around these days are kind of over 2014 or so. And then this other video on the left-hand side it's very promotable, but not very viral. What is it about? It's a Portuguese video blog about how to make pizza. And you wonder what this other dot is. It is a mathematical blog video about 31 different kinds of infinities. It is not very promotable, as audience here, I think, might appreciate. But then it's well made, therefore it has viral potentials, and it does generate lots of views per mention. Right? So what this also says that viral video got viral not just because how it inherently is, but also because of chance and what happens in external promotions. Unfortunately, views and popularity are not very predictable, which in the subsequent few years, we did neural network version of this, deep learning version of this, and its performance gets better, but interpretability doesn't necessarily get better. And then we looked at another quantity. So we were looking at the green curve. Now here's a blue curve that one of my students, Siqi Wu, now she's an assistant professor at Indiana University. So this was his first paper. He took this fresh view. He's like, oh, there's also this view watch time series. Let's do something about that. So this blue curve is basically how many minutes the whole world spends on that video each day. We joined this with a bunch of other video metadata and concepts that were extracted and released by Google. What we can, there are two informative metrics we extract from this. Basically, if we average all the video number of views over the day, we can look at how many seconds average user spent on this particular video, and also normalized by the length of video, what's the fraction of video people finish. We have lots of interesting observations on this. Basically, longer video, the smaller the fraction people watch, but on average, the time people spend on the video still increases, which is not surprising on hindsight. But what that also says, is this particular quantity different? So we essentially predict the average time watched for each video with R-square on holdout data of 0.77. So that's pretty high. Views are not predictable, but how much time we spend is very much predictable. Moreover, we found that user reputation is the dominant feature, and then topic features. Actually, content is somewhat predictive, perhaps somewhat surprisingly. And then we examined the 500 top content features. We find that generic features such as baseball, music, and books are not predictable. Y-axis is basically top of y-axis is not very informative. Bottom of the y-axis is informative. These data were from 2016. So at that time, the concept Bollywood was informative but indicative of low engagement. But the concept Obama was indicative of high engagement, where people finish lots of the video. All right. So in the three-part empirical sort of examination of how viral videos evolve, here's another bit of observation that I hope some of you will find interesting. Basically, a lot of attention in online systems are driven by recommender systems. Some of you might work on it. And what does recommender system do, right, in terms of directing traffic among different videos? So shown here is basically one video of a pop song not too long ago that some of you might know, the Hello song by Adele. On the right-hand side, if you basically erase all your cookies, you'll see an unpersonalized version of all the songs that are recommended to you. From this, you can construct a directed graph. For example, Hello is recommended from this other song called Skyfall, right? And then Hello and Rolling in the Deep are being recommended to each other. If we examine the time series behind these songs, you can see, well, these time series are quite different. Hello has had an initial big jump because it's a major release and there's probably lots of marketing, external promotions going on. And this song induced a jump in many of the other similar songs by the same artists and also by other artists. Even for songs such as Skyfall, who were not directly listed or recommended from Hello, but were 2 steps away. So there's definitely a ripple effect. So we can construct a graph among different pieces of content. And this is just a cute picture about the graph of 61,000 music videos. If we do a snowball rollout of 2 steps from this node Hello, we can see many pop artists and many famous songs came into view. My team, Alistair Tran, was the guru of actually making any prediction task work. So he designed this network forecast or time series forecast algorithm with network, incorporating network information, and applied it to not just music videos, but also Wikipedia traffic. And we found there's using basically network information does help time series forecasting. And this was the largest network time series data set that we know about until now. So let's maybe look at a demo to conclude this empirical part. Let's say we can first look at this songs diagram. So for example, this is one of the adult songs, Rolling in the Deep. And its times daily views is shown on top. And then if I mouse over another song by Adele called Someone Like You, with the edge strength actually estimated by our algorithm, you can see that their time series are actually highly correlated. And some of these annotated temporal events for this particular example was gathered by us externally about awards and other external stimulations that this artist has got. And Hello have, like if I mouse over Hello, like in the motivating example, it has a big spike, which renders these other time series being really small, right? And you can see there's counting stars is by One Republic, but even that has a spike. And we can examine Wikipedia traffic using essentially the same mental model of there is a network of time series that will potentially drive traffic to each other. This example shows the Wikipedia traffic aggregated to hourly or daily, I forgot, of the page Kylo Ren, which is a Star Wars character. And then if you mouse over Adam Driver, who plays this character, there's lots of synchronized peaks corresponding to the release of Star Wars episodes. Yeah, and then it does, right? So the network view of time series is somewhat informative and cute to look at. Let me leave it as that. If there's any questions about the empirical models and observation of attention, feel free to jump in. Otherwise, especially the last part, when we look at relationship between the attention time series, it prompts us to ask what happens, right? What happens among a set of items? So with Marco Chung and our now PhD student, we've been looking at this for a few years now, and we have some results that we can talk about. So when we say the word market, I think there's a growing intersection between machine learning and models of economics, but maybe this is still sort of niche, right? When we think about traditional market, users or someone pays money and get back goods. This is the typical exchange. In what we call attention market or YouTube videos and other online information exchange, users pay with their time and what they get back is information, entertainment, or education. Right. Many information needs. And if we think about the traditional market, the supply is limited, the price modulates supply and demand. The scarcity is in the resource or the ability of buyers to pay. And the market maker can, according to Western, essentially free economics, market maker can have minimal power. They can just basically set up the exchange and then do nothing to influence these interactions. In the attention market, on the other hand, the supply is infinite. Once a piece of content is made, it can be viewed an infinite number of times. The price is constant. It doesn't change. It doesn't modulate supply and demand. The scarcity is in total time. And the market maker can change this interaction many different ways. We will mention recommender systems and reward mechanisms a bit, and these are still very much ongoing work, right? So in order to set this up, it's worth revisiting an old paper in the journal Science by Matthew Sauganitz, Duncan Watts, while both of them were at Columbia. This paper is called Empirical Study of Inequality and Unpredictability in the Artificial Culture Market. It's known as the Music Lab experiment. So this is really done in the early days of the internet, where they supplied 48 free songs from unknown artists to 14,000 participants, and then they separated them in different worlds in a randomized fashion. So this is real randomized control trials. So what they measure is the rank of the song in what's called a random ranking setting, where they assume then subsequently the number of downloads of the song correspond to the quality of the song versus a popularity treatment there's a few different variants that they try, basically rank the song by the number of downloads they already have and watch how this market evolves. They actually find not much correlation at all on the right-hand side scatter plot between these two conditions. Basically, if you use popularity ranking, then a good song might actually not rank in the top anymore. There is a somewhat weak correlation still. So they say success was partly determined by quality. And users can try a few seconds of this song before they decide whether they download it or not. Right. In that case, they indeed pay with their time. There's no price charge. Slightly more formally, we can describe this interaction. We call this a trial offer market that has been also studied by earlier work. The users try an item, and the probability of trying is influenced by, let's say, popularity and visibility. And then after trying, they buy or download an item with, say, a coin flip parameterized by Q, meaning the personalized or unpersonalized quality factor of the song. So what evolves in this interaction process is this quantity phi, which lives in the simplex. So we assume there is a fixed set of items on the market, and the fraction of attention they get sums to 1, right? So we call this phi item market share, and it gets updated after the user have decided whether to buy a thing and which item to try. So the trial offer market, right? The probability to try is described with the choice model common in microeconomics. So proportional to a visibility term and phi itself, let's say, with a warping factor, then you can modulate the effect of popularity or the market share feeding back on itself. So the question we ask is, what is the dynamic interactions between these visibility term, market share, and quality? Visibility, to be precise, is determined by the platform. Market share is determined by the aggregate of user actions. Quality is determined by whoever produces the song. We can think about it for now as fixed, but later on we can see whether creators can respond as well. So here's a toy example to make this more concrete. Assume we have a simple market with only 3 items. We're essentially staring at the simplex from the top. Furthermore, for simplicity, I'll just rescale the quality factor to sum to 1 so that I can also put it on the simplex. And on the right, it's basically the dynamics repeated, right? The probability to try item is proportional to visibility and market share. Probability to buy them is basically the same term, proportional to the same term with Q still stuck on the front. And if we simulate this dynamics, we can see it kind of oscillates and then it stabilizes. You wonder what happens. If you simulate this with, let's say, R equal to 0.5, and start from different points, you can see them, hey, converging to the same spot, right? So fixed points are not rare in dynamics or in mathematics. But what's happening here, right? It seemed to have a fixed point. Furthermore, we were also wondering whether these dynamics have an underlying objective function, wearing the optimization hat, right? Turns out it does. So it might be easy to look at this after the fact and saying this easy, but it took Haiqing Zhu quite a bit of ingenuity to find not just one objective function, but 2 objective functions that have nice interpretations. The first one is total utility maximization, basically quality times market share for each item. And then the second version is log utility, or known in economics, social welfare, basically market share times log of quality, regularized by entropy, basically, of the entropy of the phi. What Haiqing further discovered, again, it's kind of simpler to look at after the fact, is that these trial offer update dynamics correspond to mirror descent. update on the second objective function with KL divergence as the breakpoint divergence. Right. And with this, you can show that the stationary point for this simplified, like non-personalized version of the attention market does converge to the fixed point. So that was, oh, yeah. So to drive this point home, we can update essentially the toy graphic with an overlay of the contour of this particular log utility, regularized log utility function, and see that each of these simulation trajectories are indeed doing some sort of steepest descent on the landscape of objectives. So you might wonder, what is the economic explanation of this, right? There's lots of notation on this particular plot, but you can ignore most of them. We need this particular expression B, which a personalized version of the market share. And then, so in attention market, this is what they look like, right? So it's basically V times, well, B is new phi, just minor details. It's proportional visibility, market share, and quality. W is the size of the subpopulation who share the same taste. And as we can see, it has a positive feedback loop, right? Basically, the larger B at T minus 1 will lead to a larger B when it's rescaled. In a traditional market, such as Fisher market, that our colleague Michael Chung was the first to analyze in terms of their optimization, is that the B gets divided, right? So there's a negative feedback loop. Higher price on an item drives down the consumption of the item, and that's how traditional market works. With that contrast, I think you get the sort of an idea of the flavor of this kind of work. And now let's extend similar type of style of analysis to two-sided markets. Basically, we had this graphic where the user is interacting with the platform. The platform sets the visibility and also passes the item quality quantity for the user interaction, and the aggregate of user interaction feeds back this term 5 to the platform. And if we add the curators are able to, if they're able to adapt their practices and essentially decide what's the quality of the next item they make, then this, again, goes back to the platform, and the platform feeds the curators basically how many views they get and the visibility policy set by the platform. So we can call this a quality update. So how should the creator act, right? So this slide describes a fairly typical economic interaction. Basically, the creators would want to adjust their quality in order to selfishly maximize their own utilities. What this does is basically, the first term is assuming the reward a creator gets is proportional to the number of views they have. It's essentially the same term that we've been looking at in the user set, and then minus their cost function. Right. And this can be called best response by creators. I would say this is my inadvertent adventure into game theory, and I'm sort of learning, but if you don't care about game theory, you can just think about this. And it's simple enough that you can just stare at this, take the power derivative in your head, and realize that if we basically rename this unholy fraction in here as a shorthand exposure S, then the creator response is basically C prime Q equals S. Basically, creator will adjust their quality so that the derivative of their cost function is equal to the exposure at that particular point in time. What does that do? So in the bottom, we're looking at the familiar simplex that we were looking at a few slides ago. We start the interaction somewhere on the side unequally. And then we plot the creator's response over multiple rounds. We can see that for a smaller ad, this particular dynamic converge to the middle of the simplex, equal share among the three items, and also the quality among the three producers also converge to the same. So this is sort of an equal split, assuming the creators having the same, but rather a rather general cost function. And then if the feedback signal from the market is stronger, basically for larger R, we can see that the creators with an initially randomly sampled higher quality are incentivized to actually produce better items. So this essentially creator two in this plot increases their quality where the other creators were producing lower quality items. And this also shows in the market share plot where we start at the same spot and then we go towards creator two, which is the lower right-hand side corner. So we had this, what is the underlying potential function exercise, and I'm sure you're expecting one. So here is the potential function. It has now three terms rather than two terms. The first term is alignment between exposure recommender systems. The second term is entropy. The third term relates to production cost. As you can see, in the user platform interaction, the potential function is convex. In this case, it's not necessarily convex, depending on what the hyperparameters are. And therefore, you can have very different dynamics, as we saw. Finally, you might ask, right? So there are three quantities illustrated in this diagram. What can the platform do? They can do a lot. So here's an instance of what we figured out. So we can say the platform's role is to, let's say, decide what the recommender system does, or we can call it visibility update. It can adjust a term V to influence how much an item, where the item is ranked. And in particular, let's look at a platform strategy that actually has a movable knob. Basically, it can rank an item. Again, this is a choice model equation where the ranking can be, or the inverse of ranking, the ranking score is proportional to some external factor mu, such as recency of the content or some platform strategy or how much advertising or promotion the creators paid, times quality and also market share. And the weighting between quality and market share can also be adjusted, right? So it turns out if the platform does this, we still get, or Haixing kind of uncovered an objective function of exactly the same form, except among the three terms, the weighting is no longer R-1. R is a pair of constants that are defined by this alpha R and the learning rate, the corresponding learning rate in the mirror descent. That is to say that the joint interaction among users, platform, and creators does observe mirror descent in this landscape. So what does this mean, right? So the platform, by adjusting its hyperparameter, it can influence the underlying objective function and how the attention ends up being distributed. So as far as we saw, this is the first formal description of how much a platform can do, and I think a mathematical quantification of platform power. How does it translate to, for example, how we should regulate them is, of course, another big question that was independent energy. So changing visibility or recommender system is not the only thing that platform could do. We also have a recent work that looks at entry barriers that are naturally existing among creators or imposed by platforms. one surprising result that we uncovered was that actually charging, suppose a platform can actually charge creators for posting content on the platform and then redistribute all of those revenue among the creators, rewarding the better creators with better quality and better attention, of course. Turns out the amount of charge shown in this simulation on the x-axis, it actually determines what kind of quality distribution we have. So the different color curves are basically P norm of the quality among all creators for different P, right? So P equals to infinity means a high commission maximizes maximal quality, but then all the other creators will post low quality content. And if we had almost no commission, then it maximized the L1 norm among qualities. So there's lots of online content, but also having low quality content is bad. So it turns out charging an entry fee is one way to have a tunable knob on the quality of content as well. So that's interesting. So that essentially is all of the main, the main course for my talk. I would like to insert 2 advertisements for other projects in my lab that's been going on. The first one is to understand real-world moral dilemmas. So this is switching away from like the theoretical models and machine learning. The main question we were asking, actually asked by our philosophy colleagues was, hey, what are the moral issues people grapple with every day? Because the trolley problem is likely not what everyone runs into on a daily basis. They told us, look, there is this subreddit called Am I the Asshole, where people are required to post their daily dilemmas and other people judge them. So we analyzed those 100,000 dilemmas and we found, somewhat to our surprise, there's only 47 different type of topics that are identifiable. We verified with 2 kinds of human validation, but people perceive them in pairs. Therefore, you're looking at this tree map where the size of the block correspond to the number of posts in, let's say, communication and family and friends and relationship and so on. So to our surprise, we also found that people's judgments are quite malleable. And we're in the process of Ziyu Chen is in the process of administering surveys to do this at large scale. We also found that LLMs are actually quite good at judging moral relevance, and it might be the best thing we do other than any fine-tuned language models for new data. So the second aside or add is to what's called influence flower. It's a visualization of academic data and attention that we made over many years. So Minjiang Xin was the PhD student, also lead engineer. So shown here is a paper. I believe it's author and co-author by MT, who is team leader here. And then the red edges are basically showing the number of citations to this paper by different other academic entities, people in this case. And the blue entities are the people who are influencing or being cited by this paper. So we can actually see it live. If you go to the archive page of a reasonably old paper, you will see essentially the same thing. What you need to do is to go to the Force tab and turn on this very hidden first plugin that says Influence Flowers. And then you can flip through the tabs by looking at, well, where are the papers citing this paper is from, which institution, people from which institution citing this paper, right, and so on. If you click this archive page will take you to our website where you can further interact. You can say that, well, I believe Masashi is not a co-author, but we can look at how basically he is a co-author too. Right. Right. So for each edge, you can essentially audit which other papers are on the edge. So, right. Given that we're talking about Masashi, we can also, of course, do this for a researcher. And it's basically aggregating all their paper in academic database and then plotting it. It's easier said than done, of course. So if we click the link, we can go there. By default, it has only 25 nodes. We can say, oh, let me show me a bit more. We can see that the nodes in gray are people who have co-authored with Masashi before. And you can, well, read the nodes. You can see that this machine learning has been a fairly closely knit community. And you can see, oh, how has Michael Jordan doesn't seem to have co-authored with you, but then there has been quite a lot of citations on both ways on a wide range of topics. And we argue this is a useful way to sort of portray academic attention as, and we are both producers and also consumers of this new knowledge that are produced in this process. And also look at, it's a fine-grained way of looking at what impact means. All right. So to summarize, I've talked to you about attention on online items. We've said attention is the result of network effects and under continuous external influence. Views are not predictable, but engagements, watch times are. And the network view of online items sort of both help forecasting and also help us think about attention as an ecosystem. So in terms of this market view of attention, we looked at interactions among users, platform, and creators. We found that the dynamics performs stochastic gradient descent on well-defined objective functions, and we hope this will have other applications in attention and also similar other distributed online economies. What we're working on now are attention, we hope to work on attention market science supported by empirical data. We're tackling complex information needs in climate change and beyond using LLMs and other tools built around it. And we look at humans and LLMs in terms of decision making in moral, non-moral situations. So I would like to conclude by posting an ad. We're recruiting postdocs and PhD students and hope to expand our collaboration network as well. That's all. Any questions?
Can I ask a few a bit higher level question in the earlier part? You talked about some like earlier works on applications, but of course our surrounding world is changing a lot, and often like some work 10 years ago loses the meaning directly, but still hopefully some concepts remains. And the same concept can be applied to new environment. And can you somehow like extract that kind of essence of ideas that can be still valid in the current environment? We have LLMs around.
Great question. Thanks for it is a hard question. So I feel right. So as you can see, for a few years, me and a subset of my group, we really love stochastic processes and time series. I feel like in terms of, and time series forecasting is still a very relevant problem in climate forecasting and so on. Many other applications. So I feel like that itself, especially high dimensional time series, has not been replaced by LLMs in terms of the toolchain and the model that work well. One takeaway that I shoved under the carpet, but now I will take the opportunity to mention, was for the, I should share my screen again, sorry. Is that when we did this particular time series work and was published in 2021, We actually found that a recurrent neural architecture works a lot better than transformers. Maybe because time series is actually this one way. Like it does have a distinct direction, where in transformers, your tokens can be shuffled and yeah, the only sequential information is preserved in positional encoding. And right, so maybe I feel like this entire area will continue in the LLM age, and then you will, for different type of tasks, there may be opportunities to integrate with LLM sort of centric tools. For example, some of our, I've met Rose Yu from UCSD, some of you may know her. So she is leading a team to build climate models. She worked on a lot on like differential equations and computational models for science, but then they're doing scientific foundation models, and it remains to see how do these numerical and unstructured data essentially coexist, and how we can best make use of it.
Yeah, thank you very much.
Chao Kai Chang asked, regarding the platform, recently there's a marketing strategy called personalized recommendation. Can mirror design analysis be extended to analyze the pros and cons of personalized recommendation? Okay, great question. Let me see if Haiqing is online. Haiqing, hey, do you want to take this one? Think of if he's not sure if he's paying attention.
So one thing we notice is that the potential function actually corresponds to some meaning. So it's a so once you transform the potential function. So if we have the slides on that, so the potential function can be decomposed as attention alignment, and and the summation of the cost of the producers, and also the and also the total entropy in the market. So there's a interpretation for the potential function, so which potentially can serve as a indicator of the pros and cons of like to describe a market, like how, like what kind of, so once you have a recommender strategy, then based on that strategy, you have a potential function, and uh, you can see the like the implication of your recommender strategy through our potential function to see like what is really impacting. So, for example, it can like impact the global landscape to highly non-convex, to like to make the dynamic hard to converge, to make that in turn like make the markets like more unstable, or something else. So listen, do you have anything to add on?
Actually, I think the question is about when Q becomes Qij.
Yeah.
I remember you still have a stationary point, but I really don't remember whether.
Yeah. So for the personalized part, I guess so in this presentation we just presented the homogeneous case. So the heterogeneous case is also in our paper, like in the web conference manuscript paper. That is also analyzed, and so the implication is basically the same, and the potential function is basically an extension of the homogeneous case. So yeah.
Cool, thanks.
Yeah.
I hope that, yes. Yeah, thanks, Zhao Kai, for the question. Any more questions?
So I have a few questions. For the maybe first part and also the second part, you mentioned like the meal, the promotion. So in practice, how can you really measure it? You just use API to get the data, the data from YouTube.
Yes, thank you for going back to this.
Yeah,
This earlier work. What we did Yeah, I skipped the details. What we did was actually take, right, so I think this picture has the necessary information. Was basically fit this model at the bottom to the green curve, which is the data we download from YouTube, and it involved about 7 parameters. Some were hidden in there. Right? Basically, mu is one of the parameters.
Okay, you also have other parameters that are related to exogenous sensitivity.
So for visualization purposes, we just plot mu and assign that as the explanation for exogenous. But as you can see, this one is somewhat complicated, where S gets multiplied to mu, but then in the next step, it gets into the convolution in the second term.
Okay. Because in many cases, something is promoted, but maybe the link is not mentioned. They don't promote the YouTube video from YouTube. That's very common in China. Like in the WeChat friend circle, you promote something by mentioning the name. Because anyway, you cannot directly open it from the browser. So if you are interested, you need to use some VPN and Google the name. You can find the video.
Right, we assume
That's not captured by the data, because data can only measure if you directly click share like on YouTube, and then it's counted. If some people like tweet it or using the WeChat or any other social media that without giving the link, or if they directly give the YouTube link without like using some function from YouTube, then YouTube will not count the promotion.
That is correct. The data question, I think, will never be perfectly answered.
Yeah.
I don't always. I mean, Duncan Watts is famous for saying many things, but one of his things he said is that so you can't predict history because you can't capture everything as data.
Okay.
So in this particular case, we rely on essentially we have a large Twitter feed of, and then we filter it out to just have YouTube links. So that's one data source. The other one is basically YouTube also has this sharing as a time series.
Okay.
So this is
So
does not count indirect.
Yeah. So my second question, my follow-up question is that so this model can perfectly explain a lot of things about UGC. So how about a PGC?
Well, what's a PGC? Sorry.
UGC is user-generated contents like a YouTube, and a PGC is something like a Netflix, Disney, and they promote in other way. And I'm very interested if you can capture the extraneous part, whether you can use the same model to explain it. Of course, maybe you cannot directly download the data to measure the promotion, the times, how many times this movie or this TV drama is promoted.
Right. So I think conceptually so again, a few years ago, after we've done this work, I went to Netflix and gave a talk about it, and so what they wanted to measure, they have more data, right? They will have some data syndicates from Facebook, and their external promotion basically does not come in the time series, but sometimes it's discrete, right? If a shows on, how much do they pay to advertise it on TV or on YouTube, right? And they also wonder whether it's possible to measure the effect of highway billboards. If you have driven in the American highways, you might notice some of those.
Okay.
The question is hard, right? I think for
it may be very hard.
Market, like I think it still applies that half of your marketing money you were wasted, but you don't know which one.
Because I heard the promotion cost is very huge for like a movie, and also even for like cars. Like at least 1/3 of the total price come from the promotion. The advertisement, except Tesla.
I feel there might be a way to look at some average effect, but
especially for the model you mentioned in your second part, because for the the producer generated the contents. The platform is the creator, like Netflix, so they have some special advantage to make use of this special point. Like for users of YouTube, they need to created somehow because they don't know the underlying mechanism, the algorithm of YouTube, the recommendation. So they need to guess and to improve the quality. But if the platform is the creator, maybe they have some special.
I think certainly, right? There are all these stories about Amazon promoting its own sort of affiliated brand, and then they use that brand to make whichever new product that is easy to sell, and then they edge out the essentially small sellers on Amazon. I think that is true, but then I feel like there isn't. I haven't seen a good mathematical description of that phenomenon. We would like to look at actually online transactions, but some of it, such as even delivery services, these are all really critical. But I don't like. I'm yet in the process of learning, not having access to the platform, without having access to the platform, how much we can do, or how much, like how are we limited by not having the access?
Okay. And may I ask one more question? Can I go to the page 30, 35 or 6 where you have the larger R implies some
All right, I see.
maybe not
Oh, right,
some experiments.
All right, some simulation on this.
Oh yeah,
This one.
this one. Can we use this model or this insight to explain the current AI conference? I mean, whether we are in the larger arm case or the smaller arm case where like the quality converge and the market share converge, I don't think so. So maybe we are in the red case, the winner takes all, and because there is a cost to produce paper, right? If you think a paper is a video, because now unless it's pure theoretical paper, but we still need to pay a lot of time. Otherwise, we need really to pay a lot of research fund to produce the paper. And if the response, the feedback is large, then that means the winner will finally take all, and all other participants will generate low quality papers.
Yeah, I think yeah, the reality is somewhere it certainly does not seem to be here.
Yeah.
Maybe in like a long time ago for very small communities where you can essentially form like have enough independent judgments to have an accurate estimate of quality, and then there might be a small community who are producing similar quality. You might say that maybe in Europe 20 years ago could be like that. Nowadays, there is certainly a stronger, I would say, platform effect of publicity in terms of which work get noticed. But then whether this translates to production behavior, it's less clear to me.
Yeah, I see.
Yeah. So
yeah, I don't know the motivation either, but what I observe is like some very few papers they are really influential, and due to the topic or application or due to the author and affiliation. Now, a lot of papers they don't get any online attention, and then for the authors they don't get like a strong feedback. They don't feel like they pay a lot of time and even research budget to write a paper, and the paper is even get accepted, but no one reads the paper, so they lose the incentive to write the next paper, but they have to write the next paper.
yeah, I would say unfortunately, right? So some of the academic systems in the world essentially rewards people by amount of production. but whether you wish, but then rewarding academic production by the sheer amount of attention or citation is also problematic.
Yeah, I think
So I
so.
don't think the ecosystem should, hopefully doesn't work the same way that TikTok works.
Yeah, but I think we need to find a way to escape from this.
Yes, and the
This situation.
distribution of attention is definitely skewed. Luckily not at the core. So Haiqin actually have given me some more plots that essentially converge to monopoly, which is even
I
worse.
see.
Mm.
Okay. Thank you. Are there more questions? Okay, so then maybe let's thanks the speaker again.